Hi, everyone. My name is Emma Liu. I'm a product manager from TigerGraph. Previously, I worked at Oracle as a software engineer and at MarkLogic as a product manager. My focus area in TigerGraph is on cloud deployment on AWS, Azure, and Google Cloud, as well as containers and Kubernetes, and all the enterprise infrastructure features, including monitoring and management, as well as all the connector ecosystem. And joining me today is Xingyu Chang. Xingyu is our solution team lead, and he has been with TigerGraph for 4 years, and he is a co-author of our proprietary graph query language, GSQL. And Xingyu has been leading our solution engineering teams and created many solutions and demos for most of our major customers. He is our expert on graph solutions and algorithm with TigerGraph. Today, Xingyu will tell us how he approached geospatial search solution using TigerGraph. All right, this is today's agenda. First, we will talk about a general graph geospatial use case, and then why geospatial search with graph databases. Then we'll talk about why TigerGraph is the most performant graph database for your geospatial analytics. Next, Xingyu will tell us more on the GeoGraph concepts and how he designed and implemented, followed by the demo with visual UI for the graph search based on TigerGraph as the backend. I want to start with a real-world customer problem. Our customer from Japan, which is a ride-hailing company, gave us this problem to solve. Just imagine it's 11:15 p.m. on a Saturday night in Ginza. A big baseball game just finished, and many passengers are around Ginza area. How do we predict the taxi needs for the Saturday at 11:15 p.m.? Our customers provided us with a historical traffic information, and based on that, we came up with a predicted traffic inflow and outflow from Ginza Brand Street area for this Saturday at 11:15 p.m. And the prediction is there will be shortage of 40 taxis for about 45 minutes. And our recommended action is message these 40 taxi drivers from the nearby areas so that the demand will be met. And it's really reduced the idle time for the drivers on this ride-hailing platform. So how do we approach this? We modeled our data into grids of traffic demand, and looking at each of the GeoGrid, we're calculating how many drivers are available. And we categorize them into heat map according to the demand and supply data. The drivers from oversupplied grids will be routed towards the geolocation with less drivers. And this traffic flow prediction is based on both historical and real-time data. With TigerGraph, this type of complex real-time decisions are provided to this ride-hailing platform. Another insights from the same set of data for this Japanese customer. Just imagine one of the customer from this ride-hailing company, Yushi-san, lives in Shirokane, which is the wealthy outskirts of Tokyo. And he comes Friday night to Akihabara area, which is the electronic market, and buying the toys and television. And on Saturday night, he goes shopping at Ginza and also going to the restaurants there. On Sunday afternoon, Yushi-san takes his kids to the Tokyo Zoo. And you can imagine Yushi-san's profile may be very different from Xingyu-san, who's a young professional and without who don't have a kids. So in this use case, we're really analyzing anonymized customer movement throughout the week to understand daily, weekly, and monthly patterns. And we help our customer to build out the customer's 360 profiles with likely interest and preferences based on where they go and how long they stay and how frequently they return. What does this really do? It helps the business to plan, where to open a new sushi restaurant or where to open a new kid store. It also helps manage traffic flow in different times of the week, and potentially also providing mobile coupons for different customers based on location. This really helps increase the revenue for all the parties involved. And how we do this, again, what we do is putting the data into the GeoGrids and looking at the historical data movements for the anonymized users, and also the aggregation for the historical movement patterns for similar customers, and to generate the location-based product and marketing recommendation based on a given input user at real time. And this is done with TigerGraph engine in the back end. So geospatial analytics doesn't just stop at consumer product and ride-hailing company. Geolocation everywhere, vertical and industry. For example, in supply chain management company, you can find locations of trucks and where they are and how they are heading towards, and how to route their goods and different drivers. And in oil and gas industry, you can find the locations of all the assets and oil rigs, refinery, and all those assets have location attributes, and you can have complex analytics around that. And IoT space, including your devices and cars, and finding assets related locations is very important. And of course, in healthcare, locations of urgent care facilities and providers, and how the patients are routed towards different regions, those are all important questions for modern industries. In addition, many of the new marketing and pricing insights are also generated, are based on the locations because of the smart mobile environment. What does it really mean to have geospatial analytics with a graph database? It is really about defining the entities in a connected network, matching certain geolocation patterns. And these entities are modeled in graph database as nodes and edges. What we're really providing with graph database with the geospatial analytics is one more dimensions to your solution space. Just think about your existing use cases and some of the new use cases. Your IoT system, your mobile phone, you're increasing the solution space, and that means more capacity and features to your own product and service. Here are some of the common geospatial questions we're looking at. For example, in a ride-hailing company, who are the closest target entities like taxi drivers to customer A? And then for a ambulance, find all the hospitals in real time in this region with rare blood type, RH negative. And then for doctors, you can find the doctors nearby who are specialists in congenital heart defects. Congenital heart defects are the heart defects for babies. And these kind of analytics, complex analytics, if you're using traditional RDBMS or some other NoSQL databases, you will meet some of the challenges because those databases are not designed for these complex geo-based search questions in real time. And many times they rely on third-party index engine, and that means kind of a slowdown in search. And then there's no easy SQL for answering these questions. With TigerGraph, first of all, geospatial data is already on the graph. And TigerGraph is designed for this type of deep discovery and exploratory analytics with geodata. And our proprietary query language, GSQL, can really naturally and resolving these complex questions. So why TigerGraph for geospatial analytics? Because it's not just search that we can do, but geointelligence in real time. And modern data set really requires modern tool. It is both the existing infrastructure and the data sets, and then you can identify those hidden information and analytics that you've never imagined before with the native parallel graph database, TigerGraph. So I want to ask a question to the audience now. Raise your hand if you have thought hard about your existing application and data. Anything geo-related, which can enhance your application and your service and products? I think there's a hand button to your. Okay, I see some hands raised. That's great. I hope our webinar will help you to get to that solution faster. So I want to talk about briefly the unique TigerGraph features that it's very suited for geospatial search and analytics. The first big benefit is the real-time geo insights. Just imagine you're collecting a lot of data continuously. That's a big data. And you are looking at the movements of the people and things, all the entities in your data sets at the same time. So you really need that real-time insights. And you are also looking at the deep link relationship. You're traversing through the graph in many hops. And the TigerGraph's native parallel graph architecture enabled by MPP really helps you to resolve these geo-aware multi-hop entity relationship. And TigerGraph is already suited for many other data use cases, and you can just add the geo features very easily to your current use case. For example, if you are looking at a smart mobile location-based recommendation, those geo-enriched application is very easily achieved by TigerGraph. And again, with TigerGraph, you are able to achieve geospatial intelligence. It's not just search. And if we're thinking back a few slides back, I was thinking about talking about the problems we're trying to solve with just graph database in general with geo. That's finding entities in a connected network matching certain geolocation patterns. But really, what TigerGraph enables is you will have a solution to a much bigger problem space. You know, you can look at those geolocation patterns with even movements and with continuously increasing real-time data. This cannot be achieved by the first gen and second gen graph databases because of the architecture differences. And with TigerGraph, our solution is the first and only OLAP and OLTP platform graph database. And you can look at this transactional data as well as analytics needs to your solution. All right, next I'm going to transition to Xinyu, and Xinyu is going to talk about GeoGraph in depth.
Okay, hello everyone, this is Xinyu. So I will cover the topics from the basic concepts, a GeoGrade based geospatial solution, and also I will also talk about the difference between the very commonly used R-tree and this grid-based solution. And also I will show you the implementation details, how easily one can implement a geospatial solution with TigerGraph system, how we create a schema, how we do loading and querying. And in the end, I will show you some graphic user interface to show you both on Graph Studio and on the map visualization. Okay, so, okay, yeah. So, so the whole solution is based on grids. So the entire Earth is cut into small grids of bounding boxes or cells. Okay, so each cell has its fixed length in the unit of minute, because we know that the Earth is divided by 180 degrees in the horizontal direction. right? And each bounding box or grid, it can be represented as a vertex in the graph because everything is graph. And those grid, those small cells are just the vertices in the graph. And each vertex will have a predictable ID, such as the vertex to the grid next to the current one has like a just increment the ID by one, then you can predict the ID of all of your neighbors. And each object vertex is connected to the corresponding geolocations. We have a mapping function that allows you to map by given the longitude and latitude. We can map our objects to one of the grid on the map. Okay, so this is a graph representation of how we construct the graph based on the geolocations, right? On the left-hand side, those green squares are the geolocation vertices. And based on its locations of your object, you can connect an edge between your object and those geolocation vertices. And also, your graph can also have the typical relationship between your objects we use, like the friendship relationship or like transactions. You can have anything else with the graph. It's all integrated graph with the geolocation vertices and all other relationships. So you may want to ask, okay, so you adopted like a grid-based geospatial system. So what's the difference between it and the R-tree? So the advantage of R-tree is that it allows you like search flexibly. You can search for any arbitrary regions or shapes, right? So it's a multi-layer index system that can give very good searching performance. But this disadvantage of R-tree is that it has significant redundancy in the data storage. And when you want to update the graph, you also want to update many layer of your index system. So it slows you down when you do the update. So the advantage of this grid-based system is that it's only it's nothing but part of the graph. It's just the vertices and the edges. It is naturally integrated with the TigerGraph system. And when you run the query on those GeoGrid vertices, it also runs in the MPP way, that is massive parallel processing. It will give you very good performance. And when you do the update, you just create a nudge between the GeoGrid vertex and your object. So it's very fast in updating. And we only create those GeoGrid vertices that have an object on it. So for those GeoGrid that has nothing on it, we just don't create it. So it's very memory saving. And also it's very easy to implement and maintain. I'll show you how I did the solution with just the 3 customized functions. And the disadvantage is that we may have uneven distribution of object on each grid. Because like in a very busy district in New York City, you may have like millions of people in one grid. However, in the middle of US, like in one grid, you may have only one building or one per person. So the example solution has been implemented with these example data sets. One of them is California healthcare facility locations. It has all of the healthcare facility in California, its locations, types, address, and other details. The other data we used is the city, zip code, and location. So basically, it's the city names, the longitude, latitude, and the zip code, right? So based on all these given data, we created the graph schema like the picture on the left. Okay, so in the graph schema we have GeoGrid that on the right hand side, which is in blue color. That is the one I mentioned. That one is actually the the green vertex is on the left here. Okay, and on it we have patient, zip code, and healthcare facility, and each zip code also belongs to a certain city. So we load the data in two ways, from two. So one is on the Graph Studio. You can see it from the picture on the left. We map the input data to the schema we created in the Graph Studio. But since we also utilized some token functions, you can see that. So since token function is not supported in Graph Studio right now, so we do the loading from the console with some loading script. And in the loading script, we called a function called getGridID. That function takes the longitude and latitude, and it returns the ID of the grid vertex ID. So that's how we connect your object to the GeoGrid vertex. And after the graph is loaded, you can explore the graph just like the picture on the left. You can see many people are located in one GeoGrid vertex, and also three healthcare facilities are there too. And this single GeoGrid actually is belongs to two different zip code. Yeah, maybe it contains the border, it's on the border of two zip code areas. And both of the zip code belongs to the San Diego city. And on the right-hand side is the query implementation. And from the query, you can see that given the latitude and the longitude and the searching distance, those are three parameters. Given these parameters, we want to return all of the healthcare facilities within the range, starting from the given location. Okay, so the query calls to another tool, customize the expression functions. Okay, so the entire solution is just based on those three customized functions, one for loading, two for querying. The first expression function used for the query is called getNearbyGridID. It's nothing but given the location, longitude, and latitude, and this searching distance, it will return all the nearby grid vertexes within the distance. And the second function would be geodistance. It measures the distance between two locations, and of course, it also takes the curve of the Earth into consideration for more accurate measurement. So by looking at the logic of a query, okay, I will explain the logic of query during the Graph Studio demo later. Okay, so this animation shows the mechanism of the query. So now given a user is located in somewhere in the map. Okay, starting from the location, I will search a certain area within the distance, within the given distance. Okay, and then I can figure out what GeoGrid vertexes are covered by this searching space, this searching area. Then I can get all the GeoGrid vertexes. And then starting from GeoGrid vertexes, I can find all the nearby objects. So basically, this is a mechanism of the query, how we get started, how we search for the GeoGrid, and how we find the nearby object. Okay, so let me start the demo then. Yeah, I need to switch to Wi-Fi. Not this one. Yeah. Okay, so this is the Graph Studio. So I created this end-to-end solution just based on this and a little bit of code in the console. So here is our graph schema. You can see this one is the GeoGrid vertexes, and on it we have three other vertex types: patient, zip code, and healthcare facility. And on the edge we have the longitude and the latitude, longitude and latitude info stored on the edge. And for each healthcare facility, it has a list of attributes showing the name, type, address, and the city. Okay, and this is how we loaded the files, how we mapped the files to the graph schema as data loading. So this is actually fairly small data set because this is a healthcare facilities in California. Let me directly show you the queries. Okay, for example, this one. For this query, it takes two parameters. The first one is the patient. Given the patient and the searching distance, we want to return all of the healthcare facilities that is nearby the given patient. Okay, so the logic of this query is pretty simple. It just start from this patient, and on its edge, on this patient to geogrid edge, we can get its latitude and longitude, right? And then by utilize this function, we can find all the geogrid vertexes near to this to this patient that is within the given distance. Okay, by getting and after getting the set of geogrid IDs, I store into the a set queue. Okay, and then I start from that set queue, set of ID. I can get all the healthcare facilities on the selected geogrids, right? But one thing we need to know is that not all the objects on those geogrid are within the distance, because the searching space, the searching area may only cover a sub area of a geogrid, right? So in that case, we need to check. We need to do a checking for those objects that are on the geogrid if it is within the searching distance. That's where we utilize the third customized function, geodistance. So when the geodistance is smaller than the given number, that is from the parameter, then we'll consider that is within the distance, and we will output it to the result. Okay, then let's try to run this query from here for couple. So I'm searching a patient out of our healthcare facility within 5 miles. Okay, so you only covered it's all covered in the same geogrid. So let's try larger numbers here. Let's try 25. See, then now it covers a larger area, is a vaster area. And now the blue vertices are the geogrid, and the brown ones are the healthcare facilities on that grid. And you can also see from the attribute list, the last one, distance, is distance to the given patient. The patient is highlighted here. Okay, then let's try larger numbers. So you can see all the results. Even you search wider areas, everything is just in real time. Let's search 100 kilometers this time. And you can see a very huge graph is visualized here, that because it covered a very vast area, and on each geogrid, it may have a lot of healthcare facilities. So, okay, so this is a demo for the Graph Studio, and this is a demo for the Graph Studio. This map-based visualization we implemented on the front line, on the front end. Okay, so the cursor, the location of red cursor is actually the location of our Redwood City office, where our headquarters is. And you can see all the healthcare facilities in Redwood City and the Foster City within 4 kilometers. By drag and drop this cursor, we can see the healthcare facilities in different locations. We can move it to the Mountain View, East Palo Alto. Yeah, and on the right-hand side, it shows the statistic numbers that how many health facilities within different range, and what are the type distributions for those healthcare facility. Okay, and another thing we could try is we can increase the searching area to a larger number, right? And you can see that it's just in real time. Even I have tried a larger area, we can still get the result in just within sub-second. Really, the performance is really good. And okay, let's be more crazy. Let's try 100 here. Yeah, the result is very huge in this case. It almost covered everything from the Bay Area. Okay. So back to the slides. We are able to implement this solution with just the 3 customized functions, and I will upload this solution to our ecosystem. You can download it and play with it, and even build your own geospatial solution by yourself. It's very easy to do, and it has very good performance. You can get a nearby object in very, very fast speed in real time. Yeah, and yeah, so this is my part.
Thank you, Xinyu. That was a fantastic demo. I was really impressed, like how fast when you move around, and even with like 200 kilometers radius, and you can get like real-time results on that UI, very quickly, and you can just drag and drop, and it just appears. All the facilities appear right away. I actually have a question, like how much time did you spend on working on that solution?
If you want to create your actually, it has 2 parts, right? Mm-hmm. One part is the TigerGraph side. Actually, for a user who wants to create a geospatial solution, all he needs is just to copy over those 3 functions, tweak a little bit on the loading job, add a couple more functions in the query. Then it only take within 1 hour, less than 1 hour on the TigerGraph side, and for the front-end side, because that may take you more time because it's the customized web page, right? For someone who is really familiar with JavaScript and visualization, I think it only take about 2 to 3 hours.
Oh, yeah. Wow, that's very impressive. Like, I'm still very impressed by how expressive our jQuery language, SQL language is, and how easy it is to develop these type of solution very quickly. All right. Let's just recap on the what we covered in this webinar. We talked about how graph database is a very natural fit for your geospatial analytics. And then TigerGraph is really designed from ground up for the fast geospatial analytics. And then Xinyu walked us through the whole Geograph platform and what are the algorithms that implemented with GSQL queries, as well as the demo and on the Graph Studio, as well as the UI in the front end. So I hope everyone has got a lot of information, good insights out of this webinar. And if you have not thought about geodata in your application, start thinking now. Imagine what you can do with the geospatial data with TigerGraph in your solution. Now it's question and answer time.
Okay. Yeah, Emma, this is Victor Lee, another product manager at TigerGraph.
Our director of product management is going to help us with the Q&A session.
Hi, thanks, Emma. So this is Victor Lee.
I'll hand it over to you, Victor.
I think you cannot hear me because I've been speaking. Can everyone, can someone hear me? I assume you can hear me?
Yes, we can hear you.
Yeah, we were talking over each other. Sorry. I'm going to read out some questions. We have met numerous ones. First, somebody early on just asked what MPP is, and I'll just say that's massively parallel processing. It's a design architecture for computational systems. Someone asked, there are sort of 2 non-geospatial questions, and then we'll get to the geospatial ones. One was asking about doing OLAP and OLTP in GSQL. How do we do that? Would one of you like to answer that?
Can you repeat the question?
How do you do both OLAP and OLTP in GSQL?
Okay. So actually, GSQL is like a Turing complete query language. It can handles everything. So, and if in the sense of OLTP, so usually it requires real-time response time, right? So actually, the performance of GSQL definitely can satisfy that. And for OLAP queries, such as like a PageRank or any like a batch processing has specific business logics, we can handle that too, because you can either starting from vertex traverse the subgraph give you real-time response, or you can start from all the vertexes and handle all kinds of business logics and output the result as a OLAP query. Yeah, so it can actually can handle both.
Great, thank you, Xinyu. First GeoGrid question, or geospatial. People were really interested in the GeoGrid, and can you first explain how do you set the size of the grid?
Right. Right now, by default, the size of the grid is it's a 4 minute. 4 minute, by 4 minute I mean it's like the horizontally we have about 360 degrees, right? And vertically we have 180 degrees.
Right, so latitude and longitude.
Right. So the length and the width of the grid is all 4 minutes. 4 minutes of longitude.
And there's 60 minutes. A minute is a subdivision of 1 degree, so 60 minutes in 1 degree.
Yeah, and it's customizable before you load the graph. It's just I will also include that when in the source code I uploaded, and that is the only configuration we need to change to deploy like a geospatial search project.
Okay, so it is consistent with a global structure, not a flat map, but a spherical global map.
Right.
Correct. Yeah, okay. So let's see, I'm going down the list of questions. There were a lot related to that. I think that pretty much covered that area. How do you do area and distance calculations? Does it vary per grid cell? So every grid cell is not actually the same physical size. How does that affect our distance calculations?
Okay, so by given the starting point and the distance, we will be able to know that what grids are covered, right? So all the grids covered will participate in the traversal, and then we will just get all the objects that is located on those geogrid selected. And then further we check the distance. Okay, because some of the objects on the grid may be within the distance, some of them may be out of it. Even the grid is selected because it is selected because only the sub-region of that grid is covered, right? So we need to further check the distance after it is selected.
So if I understand, then since our grid correlates to latitude and longitude, if you just know the latitude and longitude of your 2 endpoints, that tells you your grid cell span, which grid cells you potentially need to consider. Is that right?
Yes.
And also there are sort of standard equations for calculating distance using latitude and longitude. We just implemented those standard equations.
Yes.
I think that answers most of. Somebody had a little bit more challenging question. Can you represent a route or a path in TigerGraph?
That way we will need to load that data into the graph, because we ever done POCs for some like automatic driving solutions. So because basically everything is graph, all we need is just load those route data into the form of graph. And then of course, Oh, right. We also done project like for the traffic center back in China, and we calculate that maybe a segment of road they are tend to get jammed into a certain period of time. Yes, nothing. It's nothing just but graphs, vertex and edges. So it's totally doable.
Okay, here is a question about sort of maybe our memory efficiency. Do we create grid nodes on demand, or are they all, is the full grid pre-allocated?
It's on demand.
Great,
We
okay.
only create a grid vertex for those ones that already has a vertex object on it.
Let's see. And what is the front end tool we used for that demo that had the map on it?
I didn't know that. I didn't do that part, but I think it's some. I guess I'm not. I might. Oh, the guy's coming.
Yeah, we have our front end engineer will answer this live.
So the question is,
What tool did you use to create this front-end UI?
Yeah, fancy.
okay. So actually, this one is created using the library called Leaflet. It's a geographic library and you can have your own map layer, which is currently using OpenStreetMap. So it's basically can be integrated with any geospatial visualization library.
Yeah. Okay, and here's a tougher one. While you're on that topic, is the grid, is it only for a Mercator projection? Do you know what that is? Where you think of latitude and longitude actually as a rectangle, so the poles get stretched out. Does it work only with Mercator projection, or can it work with some more sort of curved space projections? Or you're not don't know.
Yeah, I think we need to look into that question more, and we'll email you back with the answer.
Okay. What will be included in the downloads that our viewers can get?
So we will upload the source code for the Graph Studio part that's
Also,
on the back ends.
And we can also help the user to deploy this system, right?
This is kind of temporary solution.
Yeah, so I think as first stage, we'll be uploading the GSQL queries that Xinyu showed. And the second stage, we'll be having this application on our test drive so that people can test it out. And the code for the front end, we might be making it more production ready and help you guys to get to this as soon as possible.
Okay, will any of this be included in the standard product or available as a separate add-on?
So currently, Victor, do you want to take this question or? Okay,
as product manager. So I said, like with all of our Graph Guru webinars, we give you the code, the source code and the sample data that we use in the demo. So everything that Xinyu showed on Graph Studio is included. That is, it was, as he mentioned, how long it took him to create it. It was for him, maybe an hour or so. So there's actually nothing special needed to do geospatial search and geospatial analytics. To do this front end with the map of the Bay Area and plotting the points, we did use an additional tool. Renshu, is this an open source tool?
The Leaflet is open source, but we also use the Mapbox API to retrieve the geographic layer. That one need if you want to use it, you have to get a commercial license.
Okay. So, at this point, we're not planning to market this as a separate product, but we can provide advice, documentation on how we implemented this. And let me see, we had maybe a couple more. We had a lot of questions today. I'm trying not to miss anyone. Some of them were similar. let's see. Hope this actually, I'm trying to figure this one out. When we mapped the source data into the graph, city and zip code were originally fields within a table, but then we mapped them into vertex objects. So they changed from just being an attribute into a vertex object. Do we have a tool that helps to do this?
To do the mapping?
Yes.
Oh, the mapping is done in the Graph Studio, basically. Like, these guys. Okay, so this, for example, this is how we connect city to zip code, right? Because we have a zip code file that having the information of the zip code number and the city name. Then I just, this is how we create an edge from the city to the zip code.
Create another one to show them.
Another one, this one?
Create a new one, maybe from city.
Oh, create a new one, yeah. Yeah, I can give you example, like create a new one here. Yeah, then I can use this column as a value of zip code and use this column as a value of the city. Yeah.
Okay. So I think the basic idea, which is consistent for how we always model and import data, the user sort of selects what objects they would like to have and makes those vertex objects, what kind of connections you want. And then the mapping is done by this drawing arrows between the boxes. So it's very easy and very visual in Graph Studio. So there's no hand coding. Even if you were to write this out in GSQL code by hand, it's actually still very straightforward to just say, I want to make zip code a vertex type. Here's the data it takes. So and that's all explained in our GSQL 101 documents. I'm going to get a couple more because we still have time. Looks like people are still adding new questions. Can this be used? Can we write GSQL from Tableau? Emma, would you like to answer that one?
Yes, so currently we can use the RESTful interface and getting the Tableau visualization that way. And we are working on on our roadmap, we're looking at the JDBC driver adding to TigerGraph so that you can get to Tableau visualization a lot more easily.
Okay, and thank you. There's a question about an alternate grid system. Do we support the quote global grid reference system as opposed to latitude and longitude?
Grid reference system. What do you mean by?
So that's in capital letters. That's why I said quote global grid reference system unquote. So I think that is just an alternate system. I think assigns ID numbers to, the grid cells. So I think the answer is we don't. This is, like I said, this was just a little application that Xinyu wrote in about an hour.
Oh, actually, for the global grid reference system, I think when we worked with Japanese customer, they actually they like frequently adopt this type of system. That they actually is actually identical idea with our grid system. However, they use a different set of numbers on their grid. Actually, the one Emma showed in the slides, the Japanese customers we mentioned, actually their project is based on that global grid reference system, other than this automatically generated grid system. Yeah.
So we could support that.
Yeah.
Okay, here's a general question for Emma. Do you partition the graph in a distributed environment?
So we support multi-graph. Is that the
No, do we partition the graph or can we partition the graph in a distributed environment?
Yeah.
Yes, we can.
So this is a graph sharding question, right?
Yeah.
Yeah, we randomly sort the graph and evenly distribute the graph across the cluster.
Let's see, and basically container image. Okay, somebody was asking if we could package the whole demo as a container, like a Docker container. That's a request. So
Yeah, okay, that's good feedback. We can think about whether it's possible because there are some of the commercial software licensing in the front end. So that's something that we need to look into. So it's possible, it might not be possible to do the container right away. But as I said, that we can put that up for a test drive environment that you can, which is hosted on our system, that you can access and look around. Yeah.
Let's see, and this is an interesting question. I'm trying to figure out exactly what, I'll just read it and see if how you would answer this. Is the storage in graph better if we have more attributes for each node?
Of course, yeah, yeah. So the question is, if we have more attribute on the vertex. So the thing is, usually by storing larger amount of attribute won't significantly slow you down. However, it will take more memory because usually we put the graph in memory, right? So so if you really need to like display it and have it participate in your calculation, of course, it is recommended to store it in the graph, right?
Mm-hmm.
Yeah, but yeah.
So one thing I'll point out is that one of the benefits of TigerGraph is that we have a compressed encoding of our data. So when you compare how much memory and how much disk it takes to store a graph with TigerGraph, it's usually at least 2 times smaller than one of our competitors. And actually, the more attributes you have, usually the higher compression you get. So when you're asking, is it better? One advantage is you usually end up with more compressed data because just the graph topology takes a certain amount of space and there's only so much compression we can do with that. But we can do even more when you have more attributes. I think there's maybe one more general question, and then some are getting very specific, and I think it would be kind of hard to answer online. So we will sort of get back to those individuals. So one is asking about they are modeling a synthetic power grid, and we do have a real world use case with that. They're modeling substations, power generators, etc. Since they have a complex topology, can they use 2 graphs to leverage the problem in the open source version? The first thing I'd say, if the person asking the question meant, can they use 2 copies of, when they say open source version, do they mean our developer edition? I'll point out our developer edition is free for you to download and use. For evaluation, you cannot, we ask that you not use it for commercial deployment. So it's there for you to test out your ideas, to get to know the system. It has the full capabilities of a single server TigerGraph system, limited to 1 graph, 1 user, and 1 server. For as long as you want to use it, there's no expiration date, but it's you can't put it into production for commercial use. And also, it does not support a distributed graph. We intentionally put that limitation in. But if you have a commercial application, come and talk to us, and we can give you an evaluation, a free trial of our enterprise edition. And certainly, like I said, we have, maybe Shin, you can say just a little bit about the state grid use case. Just, you could talk a long time about it, but just give a few highlights of State Grid.
Yeah, briefly, they actually constructed their own graph based on the devices, the power generators, the poles, all the like power consumers all the devices into a graph. And they did something like power flow analysis, running very complex mathematical formulas in the query language. And then they also do something like impact analysis. If I shut this generator off, what districts are impacted? So something like this.
Right, and so I forgot to mention who is State Grid. Maybe you could explain who is State Grid?
Oh, State Grid.
Okay, let me take that one. State Grid is the world's largest power grid, supplying power to 967 million citizens of China. It's got $363 billion in annual revenue, and their entire power grid is modeled and managed for power bottlenecks, outages in real time with TigerGraph. So it's the biggest deployment of Internet of Things or IoT sensors that is in production, graph or otherwise. And we have a case study. So please go to tigergraph.com. And if you look at resources, right on top, you will find, for instant download, State Grid Corporation of China case study. They call it the faster than real-time energy management system. And I'll explain that for a moment for those of you who are wondering what faster than real-time means. For a typical SCADA supervisory control cycle, data acquisition cycle, it's 5 seconds. State Grid Corporation of China's energy management system built on top of TigerGraph computes, takes inputs from all parts of the grid, and computes the current state, the future state, the bottlenecks, and what the plan would be to fix the bottlenecks, all in 1 second, which is about 20% of the 5-second time. So when we say faster than real time, or rather when State Grid says faster than real time for the EMS system, they're comparing that with the 5-second cycle time for a typical SCADA system. If you want to find out more, please do read that. That's a nice, we also have a research paper that was submitted by State Grid team and a host of other information. If you're considering implementation of Internet of Things of any sort, in energy management system, in industrial, in manufacturing, in heavy equipment, TigerGraph is a solution that has been proven to scale for the biggest problem in the world.
All right. Well, we're at the top of hour, and we really appreciate all the enthusiasm and all the questions. And for questions that we haven't addressed, we'll reach out to you. And here's additional resources. And stay tuned for next year's Graph Guru. And happy holidays.
Bye.
Happy holidays, everyone.